All right, let's dive right in. Picture the early days of the digital world. You had phone calls on one network, data on another, video, well, that was its own beast. It was a total mess. The big dream, the holy grail, was to create one single super fast network that could handle everything. But how on earth do you even start to build something like that?
I mean, that was the million-dollar question for engineers, wasn't it? How do you design a network where a live, crystal-clear phone call doesn't get all jittery and broken up just because someone else is downloading a massive file? The solution had to be fast, it had to be smart, and most importantly, it had to be predictable.
And the grand vision, the ambitious blueprint for this unified superhighway had a name, ISDN. You can just think of it as the master plan. It was this idea that we could build one network from the ground up, designed for high bandwidth traffic, seamlessly blending voice, video, and data together.
So, you have this amazing blueprint, ISDN. But what's the engine that's actually going to power this thing? Well, that's where a really revolutionary technology called Asynchronous Transfer Mode, or ATM, comes into play. And trust me, this is where things get really, really clever.
The entire foundation of AM is built on one incredibly simple yet totally brilliant idea: standardization. The idea was, what if we took every single piece of information, whether it's a tiny snippet of your voice, a piece of a web page, or a frame of a video, and we put it into a standardized box, a sort of digital shipping container they called a cell. And that standardization, that powerful idea, all starts with this one magic number: 53. That's it. Every single ATM cell, no exceptions, is exactly 53 bytes long. And this fixed size, well, that's the secret sauce to ATM's incredible performance.
So each of these 53-byte cells is split into two very specific parts. You've got a tiny 5-byte header, which is basically the shipping label. It has all the addressing info. And then you have the 48-byte payload. That's the actual cargo. That's your data. Okay, so why is this fixed size such a huge deal? It's all about predictability. See, with other networks that use variable-sized packets, a network switch constantly has to stop and figure out how big each incoming piece of data is. It's complicated. But with ATM, the hardware knows every single container is the same size. This means switching can be done in hardware, making it blazing fast and super simple. It also means you get very low, predictable delay, or jitter, which is absolutely essential for things like smooth phone calls and video streams.
So let's zoom in a bit on that 5-byte header. Because this isn't just some dumb address label. No, this thing is an incredibly intelligent piece of engineering that directs all that network traffic with military precision. You can see that tiny 5-byte space is packed to the gills with information. You've got fields for managing data flow, for identifying what kind of data is inside, and even for setting a priority for the cell. But for our purposes, the most important ones for getting data where it needs to go are the VPI and VCI, and the most clever part is definitely the HEC.
Probably the easiest way to wrap your head around the virtual path identifier and the virtual channel identifier is to think of them as a two-part address. The VPI is like the zip code. It gets the cell to the right general neighborhood. And the VCI is like the specific street address, getting it to the exact right house. Together, they tell the network precisely where this cell needs to end up. But here's the catch. That VPI/VCI address has to be 100% perfect. What happens if a little bit of noise on the line corrupts it? That's where that last byte of the header error control, or HEC, comes in. It acts like this unbreakable mathematical seal, guaranteeing that the address is correct.
I mean, just imagine the chaos, right? If even a single bit in that address gets flipped by some random interference, that cell could be shot off to a completely wrong destination, or more likely, just get dropped and disappear forever. For a phone call or a video conference, that's a total disaster. You got to protect that header.
And the protection mechanism is that HEC field. It uses this really powerful technique called a cyclic redundancy check, or CRC, to create an 8-bit checksum. Now, this checksum is so effective that it can not only spot if multiple bits have been corrupted, but it can actually correct single-bit errors all by itself, on the fly. It's pretty amazing. Now, the magic behind this whole check is a specific mathematical formula. And don't worry, you don't need to understand the math here. Just think of this polynomial as a secret key. The sender uses this key to lock the header, and the receiver uses the exact same key to try and unlock it. If it unlocks, you know it's authentic. It's basically the secret handshake of the network. So how does it actually work? Well, it's essentially a fancy kind of long division done in binary. The sender takes the first 4 bytes of the header, runs this special division using that secret formula, and whatever is left over, the remainder, becomes the 8-bit etch checksum.
Let's break that down real quick. So the sender takes the first 32 bits of the header, sticks 8 zeros on the end, and then divides that whole thing by that pre-agreed upon number from the formula. The 8-bit remainder that it gets back is the checksum. It then swaps out those 8 zeros with this new checksum, creates the final 5-byte header, and sends it on its way. Now, on the other end, the receiver gets the full 5-byte header and does the exact same calculation with the exact same formula. And here's the beautiful, elegant part. If the header arrived perfectly, without a single bit out of place, the remainder of that division will be 0, a perfect 0. If it's anything else, the receiver knows instantly that an error happened along the way.
But the heck is even smarter than that. It's actually pulling double duty. Beyond just checking for errors, it has a second, absolutely vital job: cell delineation. You see, in a massive, non-stop stream of ones and zeros flying down a fiber optic cable, the network needs a way to figure out where one 53-byte cell ends and the next one begins. The predictable HEC pattern helps equipment lock onto that cell structure.
So we have our perfectly sized, perfectly addressed, and perfectly protected cells. Let's put this all together now and see how this system creates an incredibly fast network.
Okay, so an ATM switch receives a cell. It runs that HEC check, and boom, it comes back clean. The switch doesn't have to waste time thinking. It just glances at the VPI/VCI, looks that up in its internal routing table, and instantly forwards the cell to the next stop, all at pure hardware speed. This happens along a pre-established virtual path that was set up the moment the connection was made.
And that brings us right back to the big payoff. This entire system, the fixed cells, the smart headers, the instant error checking, it all results in a network that is incredibly fast. It has very low, very predictable delay, which is perfect for voice and video, and it can efficiently mix that real-time traffic right alongside huge data files, solving the exact problem we started out with. Now, while you might not hear about pure ATM networks as much today, its design was absolutely revolutionary. So I'll just leave you with this question to think about. The next time you're on a perfectly clear, flawless video call, think about how the core principles born from ATM that focus on fixed-size packets and quality of service still quietly shape the internet that we all rely on every single day. Thanks for joining me.